Electric machines are a method of converting energy. Motors take electrical energy and produce mechanical energy. A direct current motor is a type of electric machine that converts electrical energy into mechanical energy. DC motors take electrical power through direct currents and convert this energy into mechanical rotation. DC motors can vary in size and power from small motors in toys and appliances to large mechanisms that power vehicles, pull elevators and hoists, and drive steel rolling mills. The essential parts of this motor are a stator and an armature. The stator produces the magnetic force that causes the rotor of a brushless DC motor to spin. It is either inside and surrounded by the rotor or outside enclosing the rotor. Other parts include rotor, brushes, commutator, field windings, yoke, poles, teeth or slot, etc. The armature coil is the rotating part, whereas the stationary part is the stator. In this, the armature coil is connected toward the DC supply, which includes the brushes as well as the commutators. The main function of the commutator is to convert the AC to DC, which is induced in the armature. The flow of current can be supplied by using the brush from the motor's rotary part toward the inactive outside load. The arrangement of the armature can be done in between the two poles of the electromagnet or permanent. A DC motor is based on the idea that when a current-carrying conductor is placed in a magnetic field, it produces mechanical force. This force direction can be decided through Fleming's left-hand rule as well as its magnitude. The stationary set of magnets in the stator used in a simple DC motor and the coil of wire with a current running through it generate an electromagnetic field aligned with the center of the coil. One or more windings of insulated wire are wrapped around the core of the motor to concentrate the magnetic field. The windings of insulated wire connected to a commutator applies an electrical current to the windings. The commutator allows each armature coil to be energized in turn, creating a steady rotating force, also known as torque. When the coils are turned on and off in sequence, a rotating magnetic field is created that interacts with the differing fields of the stationary magnets in the stator to create torque, which causes it to rotate. These key operating principles of DC motors allow them to convert the electrical energy from direct currents into mechanical energy through the rotating movement, which can then be used for the propulsion of objects. Moving on to the principle of speed control of DC motors.
The relationship of the speed of the DC motor can be derived from the equation of supplied voltage and back EMF of the DC motor. Here, V is the supplied voltage, EB is the back EMF, IA is the armature current, and RA is the armature resistance. In the next equation, P is the number of poles, phi is flux, N is the speed of the motor in RPM, Z is the number of armature conductors, and A is the parallel paths. From those equations, we derive at the relationship of the speed of the motor. For a DC motor, A, P, and Z are constants. Thus, the relationship shows that the speed of the DC motor depends upon the supply voltage, the armature circuit resistance, and the field flux, which is produced by the field current. In practice, the variation of these three factors is used for speed control. Therefore, there are three main methods to achieve speed regulation, which are armature resistance control, flux control, and armature voltage control. The armature resistance control is based on the principle that the speed of the motor is directly proportional to the back EMF. If the supply voltage and the armature resistance are kept at a constant value, The speed of the motor will be directly proportional to the armature current. In this method, a variable series resistor is put in the armature circuit. Figure A shows the process of connection for a shunt motor. Here, the field is directly connected across the supply and therefore the flux is not affected by the variation of external resistance. Figure B shows the method of connection of external resistance in the armature circuit of a DC series motor. Here, the current and hence the flux is affected by the variation of the armature circuit resistance. In the flux control method, a rheostat is connected in series with the field windings. The purpose of this component is to increase the series resistance in the windings, which will reduce the flux, consequently increasing the motor's speed. Figure A shows that in the shunt motor, speed can be controlled by connecting a variable resistor in series with the shunt field winding. Figure B shows the method to vary the field current of the series motor. First is a variable resistance connected in parallel with the series field winding. Hence, a portion of the main current is diverted through the variable resistance. The second method uses a tapped field control. The final method of speed control is armature voltage control. The speed of the DC motor can be controlled by varying the applied voltage to the armature. The variable regulation method is typically used in shunt DC motors. There are two ways to achieve voltage regulation control. The first is connecting the shunt field to a fixed exciting voltage while supplying the armature with different voltages known as multiple voltage control. The second is varying the voltage supplied to the armature known as the Ward-Leonard method. This system of speed control works on this principle of armature voltage control. In this system, M is the main DC motor whose speed is to be controlled and G is the separately excited DC generator. The generator is driven by a three-phase driving motor which may be an induction motor or an asynchronous motor. The combination of AC driving motor and the DC generator is called the motor generator set.
That is all for our presentation on DC motor and its speed controlling. Thank you.